Hello, my name is Isabel Dixon and I'm going to be talking about matrices in Gaussian elimination. The first time that matrix was referred to by matrix was in 1850 by James Joseph Sylvester. However, matrices were first used between 300 BC and 200 AD in a Chinese text called 9 Chapters of Mathematical Art by Cui Chang Sun Shu, written in the Han Dynasty. This had the idea of determinants and solving systems of equations with a matrix. Gaussian elimination was named after Charles Friedrich Gauss, who further developed matrix theory in the late 1700s, including matrix multiplication, inverses, and Gaussian elimination. Although Gaussian elimination was first used in Chinese texts, it was rediscovered by Gauss. A matrix is a rectangular array of numbers or symbols which are arranged in rows and columns. The numbers in the matrix are called elements. If the matrix has only one row, it is known as a row vector. Conversely, if the matrix has only one column, it's known as a column vector. A matrix can represent a system of linear equations as shown here. In this matrix, the coefficients of each variable, represented by A, contribute to the value of B, and are placed in the same row, with each variable corresponding to a separate column. More specifically, I'm going to talk about Gaussian elimination. Gaussian elimination is a method for solving systems of linear equations by transforming the system's augmented matrix into row echelon form. A leading entry is the first number in a matrix in RAF form that is not zero. All leading entries in a matrix have to be in the column to the right of the leading entry above. The number does not have to be in the column consecutively next to the previous, it only has to be on the right of the previous entry. For Gaussian elimination, there are three types of row operations or transformations that a matrix can undergo. These are addition or subtraction of one row on another, multiplication or division of a row, or to swap two rows. These are used to make the entries below the pivot or leading entry 0. There is also a reduced row echelon form, which still has leading entries, but the leading entry of each non-zero row is now 1. Additionally, all rows that contain only zeros are at the bottom of the matrix, and each column that contains a pivot has all other elements in that column equal to 0. Back substitution can be done on a matrix in row echelon form or reduced row echelon form to solve for the variables starting from the last row, so that you can use known values for the variables to substitute into higher rows. In turn, this will give the unknown values for each of the variables from the initial linear equations. Here is an example of solving linear equations by Gaussian elimination. First, the linear equations are converted into a matrix and then Gaussian elimination is started. For the first step, the first row is kept the same because it already has 1 as the leading entry, so the second row is focused on. 2 times the first row is taken away from the second row to give a 0 in the first position. For the second step, 3 times the first row is taken from the third row to also give a 0 in the first position. Then the second and the third rows are swapped, leading to the next step, which is to multiply the second row by -1/2 to give a 1 in the second position of the second row, which is also a leading entry. For the next step, 3 times the second row is added to the third row to turn the second number in the row to 0. Then, the third row is multiplied by 2/5 to give 1 in the third column as the leading entry. For the final answer of this example, the matrix from the previous slide is converted into linear equations for each row to be solved. Working from the lowest row up, where z equals 34/5, each newly found variable can be substituted in to find the next unknown variable. Overall, this gives x equals -5, y equals 18/5, and z equals 34/5. There are also applications of Gaussian elimination within maths, such as solving systems of linear equations, which was seen on the previous slide, and is helpful for large systems. For matrix inversion, where Gaussian elimination is used to find the inverse by using an identity matrix and converting the original matrix into an identity, leaving the once identity as the inverse, and to determine the rank, where the rank is the number of linearly independent rows or columns in a matrix when it is in REF form. There is also applications of Gaussian elimination in the real world, including in engineering, where Gaussian elimination is used to solve systems of equations for structural analysis, fluid dynamics, and electrical circuit design. In economics, where it can be used for solving models with multiple variables and in optimization problems, and in computer science, where it is used in machine learning for regression analysis and algorithms for solving large systems of problems. Here is a slide containing my references, and thank you for listening.